Hey, how's it going?
Good. The presentation said minimum 2 analysis we have to do,
Yeah. Mhm.
or only 2?
Minimum 2,
Minimum 2.
but
Okay, cool.
just stay mindful of the overall time of the presentation. Happy Wednesday. How am I holding up? I'm okay. I'm tired, just like I'm sure all you guys are. How are you? How are you holding up? Hmm. It's 4 o'clock, so let's go ahead and get started. All right, good afternoon, everyone. How's everyone doing today? Good, good. Yeah, we're winding very quickly winding down. So next week will be our final presentation. So today will be the last day you'll hear from me. So that would be that's exciting. Okay, so the plan for today is we're going to finish up our lecture notes on biomechanics of balance. Okay. You know, I say that there's not that much left of it, but you know, we'll see. But if we end early, you know, we end early, and that's fine. Okay. The other thing I want to announce today is the signups for the final presentations are going to go out after the lecture today. Okay. And so at 5:30, you're going to receive an email from me with the link to a Google Doc, and then you can sign up for a presentation slot on that Google Doc. Okay. So make sure you sign up for one, and then you know, you can either sign up for Monday or Wednesday. And then the order is going to be posted on the Google Sheet as well. Okay, so keep an eye out for that email. Only one person in your group has to sign up for a time slot, but just, you know, make sure everyone signs up for one. Okay, and if I don't see your name on the list, you know, by tomorrow, then I'm just going to start filling it in, and then I'll send the final list out to everyone after the you know, once it's all filled. Okay. So if you want to go on a certain day, you know, either Monday or Wednesday, you know, make sure you sign up for that day. Okay. All right. Another announcement I have to make is, you know, I realized we didn't actually talk about the midterm yet, and so I did have a couple people have to take it over the Thanksgiving, and so I couldn't say anything about it until that's done. But now that's done, so everyone's taken it, and now we can talk about it. So I do have the exams today, and so if you're in class today, you can pick it up before you leave. But if you want to see your exam and you're on Zoom today, then you can either come by my office or you know, I'll bring it next week as well. Okay. In terms of the average, you guys did really well. And so the average on the exam was 39 out of 50. Okay. So overall, that's right about perfect. So I think that's a really good average. So, you know, there's definitely, you know, a lot of people who did really well, and then just on average, it's really good. So yeah, great. I think it was a great midterm overall. Okay. All right, and so that's all my announcements. And so, are there any questions I can answer before we formally get started? Okay. All right. So let's go ahead and get rolling. Okay. All right. And so on Monday we left off. We were talking about the biomechanics of balance. And the whole idea with this unit is, you know, we wanted to talk about how the body keeps itself upright. Okay. Because it's not as you know, it's not as trivial, I think, as people think, right? So people kind of stand up naturally, they sit down, and you know, most of us stand up straight, you know, especially when there's no alcohol involved, right? But underneath, you know, the body's actually doing a lot to keep itself balanced. Okay. And so last time we talked about this idea of the base of support, right? And so the base of support, remember, this was the area that's basically drawn out by your feet that are on the ground. Okay. Okay. And so, you know, if you stand up right now, or you know, you have your feet on the ground, right, and your 2 feet are kind of like this. Okay. Okay. I mean, your base of support is simply just if you draw just a rectangle around your feet, you know, that's the base of support. Okay. And the idea with the base of support is that, you know, as long as your center of mass or your center of gravity stays directly above your base of support, then you're going to be able to keep balance. Okay. And the reason for this was that, as long as your center of mass stays within that base of support, then your feet or, the whatever part of the body you have in contact with the ground can produce a counteracting moment, to kind of restore you in balance. Okay. Right? And so remember, because we basically drew this image. Right. And so as long as your center of mass stays, right here, right, and so the weight of your body is going to be acting towards down that way like that. Okay. As long as you can produce like a normal force on both sides of the your weight, right, then you're going to be able to restore balance to yourself kind of no matter what. Okay. Okay. Because once your center of mass falls outside the base of support, then your body is just going to keep rotating because there's nothing that's going to be able to counteract that rotation for your body. Okay. And so if we have someone that's about to fall over, okay. Right, so let's say its center of mass is right here, okay. And the normal forces from the ground act like that, okay. If we take this as the pivot, right, we take that point as the pivot, and that makes sense because if you're kind of leaning off to one side, your body's gonna be rotating around that one foot that you have planted on the ground, okay. If we consider this normal force and this weight, okay, you can see that they produce a moment in the exact same direction, right? And so, because they're all rotating, they're all basically producing a clockwise moment around the pivot, then the natural thing for your body to do is just to simply rotate. Okay? And it's going to rotate with some angular velocity omega bar. Okay. Right, but if your center of mass stays within your base of support, then the normal forces from the ground can counteract that, and you can kind of restore your balance kind of wherever you need to. Okay, and so balance, a big part of it, of course, is where your feet are planted, right? And so if you have a wider stance, that's going to help you to have a wider base of support. But the other key thing for balance is your core muscles. Okay. Because your core muscles prevent basically this thing from happening on the right, okay? And so your core muscles help to keep your body kind of upright and straight and helps keep your center of mass kind of as centralized on your stance as much as possible, okay? And so it's a combination of both, what your lower body is doing and what your core is doing, okay? All right, so that was just a review of what we went over on Monday. So today I want to go over one more example just to kind of show you one more calculation with the basis support calculation. And then we'll talk more qualitatively on what your body can do to restore balance for the cases when you actually start to lose balance. Okay. All right, question. So if center of mass is going perfectly onto the pivot point, the body can go back up and not lose balance. Yeah. So that's so if the center of mass is right above the pivot point, then it's still within your base of support, right? And so if your center of mass is like right here, okay, right, then this is still within that kind of that cone of influence, right? So we talked about that last time. Right? I mean, it's right on the edge, but it's still technically within that cone. And so you technically won't lose balance in that case. Yeah. Mm-hmm. All right. Any other questions on this before we do another example? Okay. All right. So let's do another example just to see kind of a different look on how to do these kinds of calculations. Okay. All right, so in this example, let's consider a situation where a person is holding a weight out in front of them. Okay, and so schematically, it looks like this. And so, of course, this looks like poor form, right? Because it looks like he's lifting that heavy weight with his back, but we'll ignore that for a second. Okay. All right. So let's put some numbers on this. Okay. So let's say that the upper body for this person okay, let's say the mass of this person's upper body is 54 kilograms. Okay. And let's assume that it acts through the ankle joint. Right. And so in other words, we'll pretend that the mass of the upper body is positioned such a way that it acts, right through here. Okay. Okay. Besides the upper body, we also have the lower body. Okay. And so the mass of the lower body we'll assume is 26 kilograms. Okay. And we're going to assume that this acts through the person's butt, basically. Actually, I kind of drew this a little bit not accurately. So maybe if I drew it a bit better. And so he's kind of bending it over like this. And so his feet are kind of like out in front of him. Like that. Sorry about that. Okay. And so I think probably from here, it's a bit more clear where, if you draw the mass of the upper body, it might be acting kind of like right here. So it's acting right through the ankles. But then the lower body mass is acting through his butt, just like that. Okay. Okay. And in fact, the distance between, or the horizontal distance between the person's butt and his ankles is, let's say that it's 25 centimeters. Okay. And so basically this distance right here, this is 25 centimeters. Okay. And we'll call this distance A. Okay. All right. In addition to that, we also have the length of this person's feet. Okay. Okay. And so the length of this person's feet is 20 centimeters. Okay. And so basically the distance between his heel and his toes is 20 centimeters. And this is important because this determines basically our base of support. Okay. And so base support is basically 20 centimeters square. Okay. All right. Another thing that we can measure is the distance between the weight and the ankle joint. Okay. And so let's call that distance right here. Okay. Right. And so the horizontal distance between the weight and the ankle, we'll say that this is 35 centimeters. And so I'm measuring everything relative to the ankle because that's obviously going to be our pivot point. Okay. And so in this problem, what we're interested in is what is the maximum amount of weight that the person can carry before they start to tip over. Okay. And so in other words, we're solving for W. And so that's the setup for the problem. So any questions on the problem setup? All right. And so the way that we're going to approach this problem is, we're basically going to take, this base of support right here, okay, and we're going to compute where the total center of mass is, and if that center of mass exceeds past the toes, okay, because obviously you can see that as we increase the weight, right? So as we increase W, then the center of mass is going to move towards the right, okay. Eventually W is going to reach a point, or we're going to increase it to the point where the total center of mass is going to be outside in this region right here, okay, outside our base of support. Right? And so we're going to treat this problem as if it were like a center of mass problem. Okay, and so the first step is to compute the center of mass of this object. Okay, and then we'll go from there. And so the first step we're going to do is we're going to compute the combined center of mass, okay? And we're going to use the ankle as our origin point. Okay? Okay. All right, because remember, when we compute center of mass, we have to have some kind of origin from which we compute our distances, right? And so, because we already have everything measured relative to the ankle anyway, let's go ahead and use that to our advantage, okay? Okay, and so let's go and compute XCOM, okay? And since this is a horizontal calculation, I'm going to use X here, okay? All right, and so we have three masses here. And so we have the mass of the lower body, mass of the upper body, and the mass from the weight that he's carrying, okay? And so for the lower body, okay, so we're gonna have M low, okay? We're gonna multiply this by the distance between M low and the ankle, right? And so if we check back from the previous page, we saw that that because the lower body mass is acting at the butt, it's acting 25 centimeters behind the ankle, right? And so we're going to multiply this by a negative 25 because that's acting behind the ankle. Okay. Okay. Next, we're going to add the mass of the upper body. Okay. And then we're going to multiply that by the horizontal distance between the basically the upper body mass and the ankle, which in this case is just going to be 0. Remember, we assume that the upper body mass is acting directly through the ankle, okay? And so that's why we multiply by 0 there. All right, and then finally we have the mass due to the weight, okay? Remember, the weight is given to us in terms of force units, and so we need to divide by g in order to get it in terms of mass, okay? And then we're going to multiply this by the distance, okay? Between the horizontal distance between the ankle and the weight, which we saw was a positive 35 centimeters because it's acting 35 centimeters in front of the ankle. Okay. All right. And then this is going to be all divided by the total mass of the entire system. So we're going to sum up the mass of the lower body plus the mass of the upper body plus the mass of the weight. So it's W divided by G. Okay. Right. And so that's the location of our center of mass. And of course, we can't compute this yet because W is still an unknown. Okay. But at least we have an expression for it. And of course, since this is multiplied by 0, we can just have that go away. All right. And so let's take a step back, right? And so remember, we said that a person is going to lose balance when their total center of mass goes outside the base of support. Okay. And we saw from the problem that the base of support is basically as long as the person's foot. Okay. And so when XCOM goes past the toes, we will lose balance. Okay. And so what we can do is we can then set XCOM equal to the length of the foot. Okay. Okay. And so we're going to set XCOM equal to 20 centimeters, and then we can solve for W. Okay. Okay. All right. And so let's go ahead and plug, go ahead and start plugging in. Okay. And so XCOM is 20 centimeters. And so we have 20 centimeters is equal to, I'm going to go ahead and actually, let me do this in terms of, let me do this in meters just to make things consistent. Okay. And so this is going to be 20 centimeters is 0.2 meters. Okay. And then we plug in everything else. And so we have a minus 6.5 plus. And so that 6.5 is a combination, or it's really just this term right here. Okay. And this is going to be plus 0.0357 W. Okay. All divided by 80 plus 0.102 W. Okay. And so we're going to multiply both sides of the equation by the denominator. Okay. And so we're going to bring this up here. And so if we do that, we get 0.2 meters times 80 plus 0.102 W is equal to minus 6.5 plus 0.0357 W. Okay. And now we have just a single algebraic equation for a single unknown. Okay. And so let's go ahead and put all the W terms on one side, and we'll put all of the non-W terms on the other side. Okay. And I will continue that on the next page because I'm out of room here. And so before I flip the page, are there any questions on what we've done so far? Okay. Okay. And so if we do that, we get 22.5 on one side is equal to 0.0153 W. Okay. When we solve for W, we get W is equal to 1470.6 newtons. Okay. Right. And so this person, based on his dimensions, can carry a weight of 1470.6 newtons before he starts to topple over, at least in that form. Okay. Okay. And so that's I wanted to make sure I do that example because it's a little bit of a different spin on the calculations that we did in last time. Okay. So this is kind of a instead of a vertical distance, we're looking at a horizontal one instead. Okay. Because you can lose balance on kind of both ways. All right. And so now that we've done the calculations in terms of how someone can keep their balance, let's talk about ways that you can actually restore your balance if you do happen to lose it. All right, so let's talk about restoring balance. And so, even though your body does the best it can to try to keep balance, there will be times when you start to lose it. Okay. But when you do start to lose balance, all hope is not lost. And so there are things that your bodies can do to kind of restore balance. Okay? And you'll be surprised that you already do a lot of these things just instinctually, and so it's kind of an instinctual thing for us to do when we start to lose balance. And so we're going to go over a couple examples today that you've probably seen before you've probably seen people do these before. but we're going to talk about, how they work and why, and why people do them to begin with. Okay. Okay. All right. And so the key to all this is the concept of angular momentum. Okay. All right. Because when your body starts to lose balance, one way that we can kind of model it, or the one way that we can quantify it, is we can say that your body is going to start rotating towards the ground, right? And so if we drew kind of a person like this, okay, we say that they're losing balance. Okay. One way that we can say is that the body of the person is rotating around the pivot foot that's planted on the ground. Okay. And then, if the person doesn't do anything and he continues to lose balance, then he's going to continue to accelerate. And so his angular velocity is going to continue increasing until his head, of course, hits the ground. Okay? And so the key to restoring balance is the fact that angular momentum is conserved for a multi-segmented body, like the human body. Okay. Okay. All right. And so the goal of restoring balance is to either stop or slow down omega body, or sometimes even change its direction. Okay. Okay. And you can do that with the conservation of angular momentum. Okay. All right. Any questions on this so far? Okay. All right. So let me write out the equation for angular impulse, which is another form of the conservation of angular momentum. Okay. And so the angular impulse equation is big T times little t is equal to I omega 2 minus I omega 1. Okay. Okay. All right. And so in words, remember what this equation states. And so on the left-hand side, what we have is big T, which is torque. Okay. We have a torque that's acting on an object for a certain amount of time, little t. Okay. And so for our balance case, the torque is being provided by gravity, right? So gravity is producing a torque, about your body that's going to cause it to rotate. Okay. And it's going to be acting on your body for a small amount of time, little t. Okay. All right. And on the right-hand side, we have I omega 2 minus I omega 1. Well, remember the product of I times omega this represents angular momentum of the body. Okay. All right. And so I omega 2 minus I omega 1, this is basically the difference in angular momentum between the initial state, which is state 1, and the final state, state 2. Okay. All right. And so, the way that this equation applies to someone losing their balance is that, if you're starting to lose balance, and so, let's say that your center of mass falls outside your base of support, that means you're going to have a positive torque being applied on your body. Okay. And so this always tells us that, in the case where you do nothing, and so you just kind of stay and kind of just let your body fall. Okay. Then, the angular momentum in the final state is always going to be higher than the angular momentum of the initial state. Okay. And so, in other words, since T is positive, okay, then I omega 2 is equal to, or greater than, sorry, is greater than I omega 1. Okay. And in the case, let's say that you keep your body completely still. Okay. And so, if you're basically what we're saying is the moment of inertia stays the same. Okay. And so if I2 is equal to I1, right, then we can cancel on both sides of the inequality. And so this tells us that omega 2 is greater than omega 1. Okay. Right. And so if you do nothing, right, and so if you do nothing, if you're starting to fall down, then you're just going to keep accelerating, right? And so if you look at snapshots, you take like a very high speed camera of someone falling down, right? And each frame, they're going to be falling down faster and faster and faster, okay? Literally moments taken before, photos taken right before disaster, okay? And so we have to do something about this, okay? And so, we're kind of faced with this conundrum where, like, because gravity is acting on the body, I omega, it's always going to be growing, right? I omega is going to be growing, from one moment to the next as you're falling down, okay? And so the trick here is to basically change your angular momentum or change different parts of it such that your omega is lower in the final state, okay? And so that's the question we're going to ask. And so even though, we have to have I omega 2 greater than I omega 1, right? So that's we can't change that. The question is, what can we do to make omega 2 less than omega 1, given that this thing is going to happen? Okay? So it's a little bit of a tongue twister. Yeah. Use a jetpack. If you have a jetpack available to you, then yes, that would help, because the jetpack would produce an opposite torque. Right? But there's actually things that you can do to avoid this. Okay? And we'll talk about some of those methods on the next page. Okay. Any questions on this so far? Okay. All right. So let's look at this term I omega 2, because it's actually not as simple as you might think. Okay. All right, so this I omega 2, this represents the angular momentum of the entire body. Okay. Okay. And the cool thing about the human body is that it's not a rigid thing, right? And so we have multiple segments, right? So we have arms, we have legs, we have necks, heads. We have all these different kinds of cool segments. Okay. And so we can actually break this down. And so I omega 2 is not just one entity for a multi-segmented body for like the human. Okay. And so we can break this down into two. We can actually break it down into a lot of components, but let's just break it down to two. Just for the just for the sake of simplicity. Okay. And so we can have one term that represents the angular momentum of your body kind of as a whole. Okay. But to this, we can have other stuff too. Okay. Okay. Right. Right. And so what this tells us is that, if we can make this term, if we can make this other term higher, right, then it's kind of being like a balancing act. And so if we make this term higher, okay, then what that's going to do is that it's going to make the other term, the body term, lower. Okay. Okay. And that's what we want, right? And so we want to stop our body from rotating, right? And so what this equation tells us is that we need to generate angular momentum at other parts of our body, to kind of offset the angular momentum from our body. Okay. Okay. Right. And so we have to generate angular momentum somehow. Right. And so let me give you kind of the most obvious thing, right? The most obvious other thing that you can rotate in your body. And I've kind of been doing it, as I've kind of been talking here, and that's your arms. Okay. Okay. Right. So you've probably seen, probably it's a lot more exaggerated in movies and cartoons, right? But if a person starts to fall over, okay. Right. So what do you usually see them do? So like if you see someone that's like standing, think of like Looney Tunes or something. Someone standing on the edge of a cliff, someone pushes them over, and what they try to do to kind of right themselves is they kind of swing their arms around, right? And so they take their arms, okay, and they swing around in a circle, okay? Okay. And so by swinging your arms around in a circle, right, then you're generating angular momentum in your at another part of your body, so that your total body, or I guess we can say your torso, okay, your torso will just end up rotating slower and ultimately, maybe hopefully reverse in direction. Okay. Okay. Right? And that's pretty cool because that's kind of what people instinctually do, right? And so if you go up and you shove someone and they're about to fall over, they're going to wave their arms around, to try to prevent that. Okay. The really interesting thing, and I think the thing that some people might find unintuitive, is that in order for you to restore balance, you actually have to wave your arms in the same direction in which you're falling. Okay. Okay. Right, because remember, we're trying to offset the angular momentum, right? And so, let's just use this example. The person's is about to fall backwards, okay? And so from this view, we're saying that the person is rotating clockwise, right? And so, more by second, he's generating more clockwise angular momentum, okay? And so we need to offset that. And so we need to take some of that clockwise angular momentum and put it into other parts of our body. Okay. And so by rotating your arms in the same direction in which you're falling, then you're taking that angular momentum from the body and putting it into your arms. Okay. And if you actually, stand up and actually rotate your arms, then you can kind of see why that is, right? And so if you kind of see me rotating my arms, you can see the natural thing for my body to do when I'm swinging around is for my torso to kind of lean forward, right? And so by rotating my arms backwards, I kind of prevent myself from, falling backwards. Okay? And the same logic goes if you're falling forwards. If you're falling forwards, you want to rotate your arms forward or towards the front so that you kind of prevent that motion. Okay. All right. Any questions on this? Okay. All right. So in theory, you could rotate your arms so fast, right? And so let's say that you have helicopter arms, right? And you're starting to fall over. You can rotate your arms so fast that you actually reverse the velocity of your body, and you kind of right yourself. Okay, and so some people can do that, but sometimes it can be hard, especially because a lot of times when you lose balance, it all happens really quickly, and so you have to have good reaction times and very fast arms. Okay. Okay. But it's hard because because your arms, relative to the rest of your body, don't have nearly as much mass. Okay. Okay. Because remember, the moment of inertia, it depends strongly on, it depends strongly on distance, but it also depends strongly on mass as well. Okay. And so if you're comparing, the amount of angular momentum that your arms can generate versus your entire body, it is very different. So that's why it can be, but theoretically it's possible if you do it fast. Okay. And so the same principle can be applied when you're trying to balance on a tightrope. Okay. Okay. And so, let's say that you're trying to, we have a person that's trying to balance, okay? So let's say that he's balancing on a tightrope here. Right? What's the natural thing that people do when they're trying to balance on kind of a short thing, right? So they stick their arms out to the side, right? So they make kind of like a T pose of this, okay? And so the reason people do this is that, is to help offset any kind of body rotations, right? Okay. Because if you're balancing on a tightrope, you might have cases where your body's going to start rotating this way, right? So let's say you start to fall, to one side. Okay. In order to offset that, you can rotate your arms in the exact same direction. Okay? Right. Same principle as you're falling forward to back, but when you're falling side to side, you rotate your arms in that direction faster in order to kind of regain balance for yourself. Okay. And the reason it's more effective to do this when your arms are out is that you increase the moment of inertia of your arms by having them farther away. Okay. Okay. Because remember, the further away an object is from the rotation point, the higher its moment of inertia is going to be. Okay. And so that's why holding your arms out makes this a lot more effective than you could just have them as little chicken wings. Okay. And so you can actually enhance this effect as well by holding a very large heavy pole. Okay, and so you might have seen that maybe Cirque du Soleil or other circus performers do this, right? And so just like same thing, you have a person that's balancing on a very narrow platform, okay? But instead of using their arms, they're holding a very, very heavy pole, okay? Something like that, right? Right. And even though that pole looks really heavy, the pole is actually there to help you maintain balance, right? Because if you compare the moment of inertia of a huge metallic pole versus your arms, right? The pole is going to be a lot heavier, and a lot of times the pole can be a lot longer too. Okay, and so by holding a big heavy pole, you further enhance the moment of inertia of your balancing act, basically. Okay? Because at least I know that when I was growing up, and I saw people holding these heavy poles, I actually thought they were making things more difficult for themselves by holding the heavy pole, because I'm like, that must be really hard to balance, but it's actually there to help them enhance their balance, because it's a tool to kind of help them offset any kind of rotations for their body. Okay, and so you only have to rotate the pole just a little bit, right? And so let's say that you're falling over to the right a little bit, and so you only have to rotate the pole just by a very small amount to right your body and to bring it back the other way. Okay. All right. Any other questions on or any questions on this? Okay. All right. And so the one other tactic we'll talk about is has to do with something else you can do with your body. Okay. And so something else that people do naturally when they start to lose balance is that they bend their hips. Okay. Okay. All right, and the logic is exactly the same. Okay, and so by bending at the hips, on the one hand, you you kind of like partially rotate your body. Okay. And this is going to absorb some of the angular momentum that the body is generating. Okay. Okay. But this actually also has another useful side effect too, in that it helps to bring your center of mass back within your base of support. Okay. Okay. And so, visually it looks something like this. So let's say that, a person's falling over, okay? And I'll make a joint at his hip, okay? And so let's say that the person's rotating this way like this, okay? Right, and so by bending at the hip, what he's doing is something like this, okay? And so basically he's going to force his upper body to rotate this way while his lower body rotates this way, okay? Right. And so in the end, he ends up with a configuration like this. And so by kind of forcefully bending at the hips, he's generating some angular momentum for the upper body. And of course, that's going to offset the total angular momentum of the entire person's body. Okay. Of course, the legs have to rotate the other way because they, in order to take this position. Okay. But usually, the legs have a lower, mass overall than the upper body. Okay. Especially since he's rotating around about the ground, right? The moment of inertia of the lower body is much lower than the upper body. And so, even though the legs have to rotate it in a different direction, they don't have as big an impact as the upper body. Okay. And the nice thing about this too is that you kind of naturally bring your butt kind of back. Okay. And this is going to naturally bring your center of mass back within your base of support. Okay. I drew him as kind of like a peg leg here, but you can imagine he has another leg right here too. Okay. And so that's kind of the other kind of natural thing that people do when they start to lose balance. Right? So if you shove someone, then they kind of like, they go like this, they kind of, rotate their arms and they do all those things to keep balance. And so, these are things you've probably seen people do before, but these are kind of the biomechanical reasons about why they work. Okay. All right. Any questions on any of this? Okay. All right. So that's all we got on biomechanics of balance. And so, I know, we still have some time in the class, but, I'm just going to go ahead and end it early. So for those of you in the class, I do have your midterm exams here, so you can come pick it up. Okay. And for everyone else, remember, I'm going to send out the email for the presentation signups at 5:30. Okay. So I think ending early now will give, people in the class a chance to get to their computers too. Okay. And so make sure you keep an eye out for that email and to sign up for the, sign up for a presentation slot when you can. Okay. So remember, only one person in your group has to sign up for a presentation slot, and just put the name of your topic in the list. Okay. All right. So thank you guys for tuning in today. This is the last time you'll see me kind of lecture for the full lecture, and then starting next week we'll have final presentations. Okay. And so if you have any questions on your final presentations over the weekend, please don't hesitate to reach out, and I'll try to get back to you as soon as I can. Okay. So have a great weekend, everyone. Come up, pick up your exam if you're here, and I will see you next week for final presentations. Oh, final presentations, you guys don't have to come in for that. So if your entire group wants to do it virtually, that's fine with me. I mean, I have a good setup here where, I can just share the screen and we can do that. And so, I don't mind whether you do it virtually or you do it in person, but just make sure everyone in your group is on the same page. So I don't want to have some people here and some people virtual, and I think that'd be kind of weird. So just talk it over with your group and see what makes the most sense. And then I'm fine with either one. Okay. All right. Thanks, everybody. Yeah. Yeah. Mhm. Yeah. So the sign up will be 5:30. So I'm going to send an email announcement with the link to the rule sheet, and then you just sign up for that. Yeah. Yep.
Quick question.
Sure.
So presentations are due the day you present, basically?
No, so I'll have the slides due end of next week. And so if you want to modify them after your presentation before you submit them, then that's fine. So I'll have them do this all the same day for everyone.
I'm sorry, it's because I have like presentation all over the place. So we're
Yeah.
presenting during finance week,
No, we're presenting next week.
next week.
Yes.
Okay.
Yeah, during class next week.
Okay, and then so presentations are due the end of next week.
Exactly.
Okay,
Yeah.
perfect. Sounds good. Thank you.
Yep. Mhm.
What's the minimum analysis we should have on paper?
Wait a second.
Minimum analysis that we have to do?
Yeah.
No, what's the minimum?
Oh, for the report,
Report itself, yeah.
for 5.
You do more?
You can do more. Yep.
Okay, cool, because yeah, we're each doing like 3 different fighting styles.
Yeah, I think,
Like, each do like 2 or 3.
Yeah. So for you guys, I think when you have more people and different styles like that, I think more makes sense. But I didn't want to put like an overly restrictive number for for other groups, so I put 5. But yeah, if you guys want to do more, then
Okay,
that's
cool.
fine.
And are we able to like to do like the analysis and take like handwritten, take a picture of it, turn it like? or
I'm fine with that, but just
Fixed it.
but make it try to make it as high quality as possible.
Possible. Okay.
Yeah. So try to make it as readable as you can.
Okay, cool. Yeah, because it's kind of hard to do like the equation.
Yeah, yeah.
like,
No, I understand. Yeah.
Stuff like that.
Mhm.
Up for us, see you tomorrow.
Okay, see you tomorrow. And Sam, did you have any other questions before I sign off? Okay, all right, I'll go ahead and close the call then.